So I'll stop a bit early. But so we've quantized Yang-Mills now. So we have the Feynman rules. That's the outcome of quantization. And what I'd like to do is I'd like to do this calculation of the running coupling constants in Yang-Mills. We do a few things along the way, some interesting insights into dimensional regularization, some more practical group theory, a little tour of some of the gauge invariance issues. Okay, so let's do. I just want to start off by reminding of the running coupling in QED. Because one of the things we'd like to do is contrast it. So when we first did QED, we started at q squared equals to 0, but here we'd like to do q squared is much, much bigger than m squared, and we'll take q squared to be at some renormalization point, which is mu r squared. So we'll renormalize at some large value. And if you recall, we had interactions in QED being, including the vacuum polarization diagram, that turns into the bare coupling squared over q squared, 1 minus this vacuum polarization function, which we summed to be 1 plus pi of q squared. But if we're doing perturbation theory, we don't really have to worry about that part. I'm not going to force that on you. Because actually in QCD it's not as easy to do that summation, and you'll see why. And the calculation was that pi of q squared, well, I had the charge squared, that was 6 pi squared. There was a 1 over epsilon in dimensional regularization, epsilon being 4 minus d the way I'm doing it. Sometimes it's d minus 4. Plus log square root of 4 pi minus gamma over 2, gamma being Euler's constant, 0.577, plus 5, 6, minus 1/2 log minus q squared over mu squared plus ... Okay, so there's what it comes out to be. If you then define the charge at this renormalization point, E squared at mu r squared is E0 squared, this 1 minus pi at q squared equals mu r squared. Then you absorb all those constants in there, and you end up with E squared at a general q squared is E squared at mu r squared 1 plus E squared over 12 pi squared log q squared over mu r squared. Okay, and let's keep it on the same page here. The beta function is the way that this coupling depends on mu r is e cubed over 12 pi squared. Are all my factors right? I think so. Okay, so there's there's our running coupling constant in QED. All comes from the vacuum polarization function. It runs, we've renormalized at some scale mu r, etc. Okay. So when we do the same thing, what I'd like to point out is that the logs here and the epsilon always tie together. So this is a trick in dimensional regularization that makes life very easy. So the divergences determine the logs. Okay. And here's why it happens. We're going to work at q squared much bigger than m squared, so m squared is not important. Okay, and you see that in the vacuum polarization there. M squared is dropped out. It's always small compared to q squared, so you just neglect it. Then mu enters only in the following way. It's mu to the 4 minus d integral d d k loop momentum okay. So we've added this dimensionful factor to keep the overall factor unchanged. So if this goes from d4k to ddk, we put mu to the 4 minus d to keep the factor the same. This tells us that whenever we do a calculation, we end up with this mu to the 4 minus d, and there's stuff along, it always comes along with, if there's a divergence, it's 1 over 4 minus d, and so that's an e to the 4 minus d log mu, 1 over 4 minus d is 1 over 4 minus d, 1 plus 4 minus d log mu, so that you always end up with things that look like it's 1 over epsilon plus log mu, or as we saw before, we saw 1 over epsilon minus 1/2 log mu squared was downstairs, and we had q squared. So mu dependence always comes exactly tied to 1 over epsilon. They have the same coefficient. Log mu and 1 over epsilon are always the same coefficient, because the only place that it arises is there. But then since the only other scale is q squared, you know that this has to then be 1 over epsilon minus 1/2 log q squared of mu squared. So the log q squared piece, which is nice and physical, mu is irrelevant, but q is physical. The q squared piece also carries the same coefficient as 1 over epsilon. So if you want to do the calculation, all you have to do is you just look for 1 over epsilon, and implies you know log q squared. So it makes it easy. You just look for where the divergences lie, and you're done. Sometimes I'll write this in the following way. I'll write this as mu squared over q squared. It's actually minus q squared, it turns out, but that's technicality. 1 over epsilon, and then I put the power epsilon over 2 there. That's again, by this trick here, by expanding, is that factor there. So that's how it always occurs. Sort of interesting. So then if G is some G0, 1 minus B0 G cubed, 1 over epsilon plus dot dot dot, when you're doing the renormalization, you automatically know the beta function is mu r dg mu r equals B0 G cubed. Okay? So one of the nice features of dimensional regularization is we'll do that. And so that just means we don't have to do the full calculations, we just pull out the 1 over epsilon. Okay, so now to do charge renormalization. Yin-yang nulls. So in the non-abelian theory. The trick here is that there's many ways to define the charge. In QED we did something that looked like this, the coupling of a fermion to the gauge boson. That works here too. We could, however, if you remember the Feynman rules, the coupling of 3 gluons is also G. The coupling of 4 gluons is G squared. The coupling of a ghost to a gluon is G. So the tricky feature is that any of these calculations had better give exactly the same results. And so we need to have various definitions. Of G renormalized. Okay. Well, the various renormalization factors that we have to do is, so if you take a fermion and look at the self-energy, that ends up going like Z2 to the minus 1 over P slash minus M. That defines the wave function renormalization Z2. Okay. If you do the same thing, self-energy for gluons, there's diagrams like that, plus diagrams like that, plus diagrams like the fermions in the loop, plus diagrams like the ghosts in the loop. That goes to Z3 to minus 1 over Q squared. So wave function renormalization for the gluon is Z3. There's a vertex renormalization which looks like that, plus that, where this is the vertex for the fermion. This goes like Z1, but there's a couple Z1s times gamma mu. So it's Z1 for a fermion. There's an equivalent one for a gluon. You do things that look like, actually I haven't got all the diagrams drawn here, but there's certainly, maybe that's it. There's of course various permutations on that. That's Z1 gluon minus 1, or gauge boson minus 1, times the basic form of its vertex, which is a long one. And then there's a large bunch of diagrams that look like that, plus a lot of other stuff, which goes into renormalization of the quartic coupling. Okay, so those are, in principle, to do this completely, we have to calculate all those guys. And so the definitions are G renormalized. Well, from the, if we did this, this to define with fermions on both sides here, that's G squared renormalized. So you take half of that, it turns into Z1 F minus 1, Z2, Z3 minus a half, G0. Okay, so the Z1 comes from looking at this vertex here. The Z2 is the wave function renormalization. You have a square root of Z2 for each external fermion line. So if I'm looking at the top line, there's a square root of Z2 from that, a square root of Z2 from that. And the Z3 comes from basically taking this diagram, putting half of it up there and half of it down there. Okay, so the Z3 to the 1/2 goes up here, and Z3 to the 1/2 goes down there because there's charges squared. Okay, so that's where all those factors come from. If you do the same thing for gluons, you get Z1 gluon to the minus 1, Z3 to the minus 1/2 G0. If you use the quartic coupling, it's Z4 to the minus 1/2 times Z3 G0. And if I use the ghost, there's a Z1 ghost. Let's make it C because G is already taken. Minus 1 Z2 Z3 to the minus 1/2 G0. Okay, so we have all these definitions, and they better all give the same result. To show that they're the same, and I was tempted to do it, I'm not going to though, is there's these Taylor identities. So there's a little formalism you can do that shows that these are all the same. But I think I'll do other stuff instead. Okay, but that's where we are. Okay, so let's go through them. They're done in different books in different ways. If you want to see the one using this vertex here, you can go to Cheng and Lee. They do a complete job on that. I'm going to do the one that's closest to what we did, where we do these guys, the fermions, because we can build on all the stuff that we've already done. So the first thing I'm going to talk about is the vacuum polarization. Okay, and the first thing there, the easiest one to do, is the fermion. Okay, so with a fermion diagram is, of course, this. We've talked our way through that one a lot of times, but I'll write it out and then focus on the color factors, or the Yang-Mills factors, which are different. So this has a gluon momentum Q coming in. Let's give it, to match the notes, give it Lorentz index alpha and color beta. Color A, this one will be B beta, and it's also Q. So the vacuum polarization function has alpha and beta indices for the external lines, has A and B for the color Yang-Mills index, and it has the following form. There's a -1 for fermion loops. Okay, remember, whenever there's a fermion loop, you have an overall factor of -1. There's the integral d4p over 2 pi to the 4th. Then if I started someplace on this thing, let's start right here and go around. At that vertex, I have minus ig gamma alpha lambda a over 2. So that's vertex. Right? So Feynman rules taught us. Then it's I over something which I can call p/-m. Then I hit the other vertex, which is minus ig gamma beta lambda b over 2. I then have another propagator, which has to be, if that's p, this is coming this way, is p minus q, p/-q/-m. And I'm back to the same point again. These guys are matrices, so when I come back to the same point again, the index that sits on this side of the Dirac stuff is the same as the index on that side, so it becomes a trace. Likewise, in color, it becomes a trace. So it's a trace of this, where that trace means both Dirac and color. Okay, so there are two separate indices, so there's two separate traces. We could write trace if you want. Okay. The Dirac stuff is exactly what we had before for the electrons. The color stuff, you'll have to let me refer to the Yang-Mills indices as color. Okay, we're doing SUN all at once, but I can't stop calling them color. Okay, the indices associated with the Yang-Mills theory. So color is trace lambda A, lambda B is 2 delta AB. And so aside from factors of G lambda over 2, and this guy, it's the same as QED. And so we end up with is I pi AB alpha beta is I q alpha q beta minus g alpha beta q squared. We get mu squared over minus q squared to the epsilon over 2 as advertised, delta AB g squared over 12 pi squared 1 over epsilon plus dot dot dot, and that's where we'll stop. Okay, so and if there's n types of fermions and f types of fermions, we get an extra factor of NF, and I'll carry that along. So there's lots of these. So these are anything in the fundamental representation. Okay. So for gluons, we have this diagram and this diagram. Okay, so I and double I. Okay, let's do double I first. The second one. This one equals 0. Okay, and the reason is that loop integral is the integral d4 k 2 pi to the 4th 1 over k squared, which is obviously infinity, but when we extend it to the integral d dk over 2 pi to the d 1 over k squared, that's equal to 0. Okay, so let's go through the usual argument that infinity equals 0. Okay, so this is a oddity of dimensional regularization. Okay. So if you take, let's just do a general case. It's integral d4L over 2 pi to the 4th 1 over L squared plus M squared to the nth power. Well, let's do those guys. This turns into, mu to the 4 minus d integral d dl 2 pi to the d 1 over L squared plus M squared squared. Okay, if we then just plug away and do this in dimensional regularization, what you do is you do the angular integral in terms of gamma functions, and then you do the radial integral in terms of gamma functions, and you can sort of see what everything that comes out. So the piece that's there's a plus I, no, it's a minus I over 16 pi squared. There's a 1 over 4 pi to the d minus 4 over 2. So I can't get to the 16 pi squared too easily, but this you can get just from watching those factors of pi and the ones that come out of the angular integral. Then there's a gamma of n minus d over 2, which is the gamma function that's left over. There's mu over m to the 4 minus d So mu is always 4 minus d. And then the last piece is gotten by doing dimensional analysis. It's m to the 4 minus 2n. Okay, if and that square there should have been n. Sorry. So if n is 2, it's L squared over. I mean this guy comes out L squared over L to the 4th over L to the 4th, so it should be dimensionless. So there's no factor of m there in that case. So, okay. But then for n equals to 0, then I take m goes to 0 to get the massless integrals. The integral d4 L over 2 pi to the 4th goes to 0 because of this m factor. And n equals 1, integral d4 L over 2 pi to the 4th, 1 over L squared goes to 0. So those are our oddities of dimensional regularization, where these things physically blow up, but calculationally they get set to 0. It doesn't seem to cause trouble, except when you think about cutoffs and use dimensional regularization, you can get into big trouble this way. So you have to really think in dimensional regularization. And I can point to you in places like in chiral perturbation theory where things are set equal to 0 because of this thing, which in the real world are not 0, but nevertheless you end up thinking they are. The converse, if I take n is equal to 3, then the integral, well, it's actually, yes, 3 is the one I want, d4L 2 pi to the 4th, 1 over L squared goes to infinity. That guy is physical. And that happens in all regularization schemes. And actually, this is L squared cubed, right? And that's physical because it happens at the lower end, where we know what the physics is. This is L to the 4th over L to the 6th. It blows up. So this has to cancel in a nice, well-behaved theory, because that type of divergence is physical, if you get it. Okay. So this sets the simple loop diagram to 0. I have to calculate the other one. Okay, for the other one, this diagram, which is this guy, we have, I'm going to focus mainly on the color factors, but let's just write out type of thing. Pi a b alpha beta of q squared is, well, there's a factor of 1/2 that comes from the Feynman rule about 1/2 for the loop of identical bosons. So that piece enters, there's a minus I g squared from the vertices. there's a minus I from each propagator, so that's squared. And then I have the integral d4k, 2 pi to the fourth. Each coupling is Fa. So let me draw this a little bit bigger here and label these. This is A, B, we'll make this C and D. F, A, C, E, F, B, D, E. No. Yeah, actually, I've got that wrong. It's my mistake. That's A, C, D at the top vertex, right? A, C, and D come together at the top vertex. B, C, and D come together at the second vertex. Okay. There's some momentum factors which I guess I won't bother writing out. K squared plus I epsilon and K minus Q squared plus I epsilon. 2 propagators. That's the thing I wanted to work on is the color factor. The color factor F A B A C D F B C D. Now that's, unless we want to work out what those FABC's coefficients are, that looks a little painful. I will show you how to calculate that. That is called the quadratic casimir for the adjoint representation. It's one of the features that categorizes the adjoint representation, is that sum, and we will calculate, it will turn out to be the number of colors, okay, and proportional to delta AB. Okay, let me do that in a second and just finish this thing. If I do the rest of the calculation on alpha beta, it turns into I 11 thirds Q alpha Q beta minus 19 over 6 G alpha beta Q squared. Then I get minus G squared over 16 pi squared, this quadratic casimir, delta AB, 1 over epsilon. And of course, mu squared over Q squared to the epsilon over 2. Okay. One of the things that you notice there is that this is not gauge invariant. Which is the Q alpha pi alpha beta is not equal to 0. So that's an indication that we've got some unphysical stuff in those loops. The physical stuff had better be gauge invariant. The ghosts, of course, are going to correct that. Okay. So but I want to, this part of the lesson is I want to do some more practical group theory. I'm going to calculate C2 in the adjoint, and I'll also calculate the quadratic casimir and the fundamental along the way. And a bunch of other calculations. So in doing this, I'm going to use this identity that I gave you before. Lambda, when we sum over these color labels, lambda A ij kl is 2 delta il delta kj minus 1 over n delta ij delta kl. Yes, okay, I think that's right, yes. Let me just think of for a minute. I take the trace ij. Yes, it works. Good. Okay, so then I have a bunch of things I want to show you. If I have lambda A multiplying each other out right next to each other. Okay, I want to take the L matrix element of that. So this is a matrix. It's just lambda squared summed over all A's. I can get that from this identity by taking J is equal to K. That becomes matrix multiplication there. So it becomes, I do delta J K on that identity. And the first term then I get is 2 times n times delta IL. And the second term I get 1 over n delta IL minus 1 over n delta IL, which you don't more often see this written as 2 over n squared minus 1. Okay, that's that guy. I want to do lambda A, lambda B, lambda A. So what happens if I have a matrix in between the two A's that are summed over? You can work that guy out from this too. That's lambda B JK of that identity up there, right? So I just put lambda B JK, sum over it becomes the multiplication of 3 of them. Okay, and the first term here, delta KJ, delta on lambda KJ, it's a trace of the lambda matrix is 0. So the first term is 0. So I get 0 there, minus, I have 2 over n. This one is IJKL, so this turns into the lambda B I L becomes the lambda matrix. So basically, when you do the sum of these two on the outside, you basically pick up a minus 2 over n times the same thing again. Then let's do lambda A, lambda B, lambda A, lambda B. That's IL. That's this thing times lambda B, which then is like up above. So that's minus 4 over n squared minus 1 delta IL times the unit matrix, and lambda A, lambda B, is 4 over n squared minus 1 quantity squared. Okay, so there's a bunch of things. So there's a bunch of practical calculations that you do encounter. Then to get C2, for the adjoint, here's how you can do the calculation. We know that lambda A commuted with lambda B is 2I FAB C lambda C. So if I take lambda A, lambda B, lambda A commuted with lambda B, that's 2I squared FAB C FAB D lambda C lambda D. But by definition, that's the 2I squared times the quadratic casimir in the adjoint, by definition, times the delta function, Kronecker delta lambda C, which is then minus 4 C2 adjoint times, I have, that's 2 over n squared minus 1. Okay, so if we do that calculation, we get the casimir. So then if we do that, then we take lambda A, lambda B, lambda A commuted with lambda B. That's these two terms that I had up there. There's two occurrences each of lambda A, lambda B, lambda A, lambda B. And then with a minus sign, lambda A, lambda A, lambda B, lambda B. So this is 2, and I have to read off my factors, times minus 4 over n squared minus 1, minus 4 over n squared minus 1 squared equals minus 8 over n squared minus 1 C2. And I'll take a deep breath and hope that the numbers all work out. So the n squared minus 1s cancel, that becomes 1 power. It's minus 4, so the minus 1 piece here cancels, and I have then n squared over n squared with a minus 8. Worked, so that cancels, and so that whole side there becomes minus 8 times plus the n squared minus 1 factor, and it works, so that it implies that C2 is equal to n. Okay, let me do two other things at this stage. For the fundamental representation, the quadratic casimir is defined as lambda A over 2, lambda A over 2. IL is C2 for the fundamental times delta IL times 1. And we did that along the way up here. That was, aside from the factors of 1 over 2, it was that first identity. So this implies that the C2 for the fundamental equals 1 over 2n, n squared minus 1. And the other thing I'm going to do for later is write the identity that we had there, lambda A, lambda B, lambda A, in terms of these casimirs, is 4 C2 fundamental minus C2 adjoint lambda B. If you plug it through, that works out. It's really just, it's the calculation that if you put in the right factors, that ends up working out. Okay. So actually, I'm going to stop there. I have to run off to my appointment. So any questions before we go? We'll come back. We'll do the ghost. We'll show how that restores gauge invariance. We'll do the vertex corrections. We'll show that they contribute here where they didn't in the fermion case. We'll put it all together and we'll have our running coupling constant. Yes?
So, so our C2.
Yes.
Casimir invariant?
Yes.
So basically it commutes with all the generators?
Well, in these cases, it's it does, because it's proportional to the identity in both these cases. And yes, so yes, it will.
Well, I thought that was the definition of Casimir invariant, though. It had to commute with all of them.
Okay, well, it does.
Okay.
Yeah, I mean, see, it has a different representation in these two cases. In this case, it's the quadratic Casimir is from this 2 by 2 matrix. In the adjoint representation, it was a matrix 1 in the n by n space that the adjoint lives in. Okay, so they has different dimensions, but it is an invariant. Okay, anything else?